Hello everyone, this is lecture 4 of week 9. In the previous lectures we were learning about simplex method. So, given a linear programming problem, we first worked on finding the vertex of the feasible polytope of the linear programming problem, right. So, that just involved choosing m linearly independent columns out of n columns of the matrix A, right. And the variables corresponding to those columns were called basic variables and the other variables were called non-basic variables. The basic variables had the solution B inverse B and the non-basic variables has the solution 0. Okay. So, after starting with a vertex, okay, we first figure out how whether the vertex that we took is indeed the minimizer or not. Okay. So, we just had to take the vector C n transpose minus C b transpose B inverse n, okay, and verify if every component of this vector is non-negative. If it is, then it is a minimizer, otherwise it is not. Okay. So, if it is a minimizer, we stop. If it is not, then we have to exchange one variable from the set of basic and non-basic variables, right. So, we take in the variable corresponding to the minimum of the C n transpose minus C b transpose B inverse n vector into the basic variable. We still have to address the question which variable has to be thrown out of the set of basic variables, right. So, we will do that now. Okay. So, note that if you take this particular equation, right, x b equals B inverse B minus B inverse n into x n, right. So, x b actually is x 1 dot x m, okay. Of course, it need not be 1 to m, but this is without loss of generality, okay. That is, otherwise you can rename the vectors as x 1 to x m, right. And this is actually, you can say, B inverse B 1. So, B inverse B is a vector and an n dimensional vector, right, sorry, m dimensional vector, right. So, this is B inverse B 1, B inverse B 2 dot B inverse B m, okay, fine. So, that is B inverse B. Now, what is B inverse n into x n? Note that x q is going to become basic in this, the others are actually going to remain 0. That is, if x m plus 1, x m plus 2 dot x capital N x little n are the non-basic variables, x q will be non-zero, all the other n minus m minus 1 variables are going to be 0, right. So, now what is B inverse n into x n? It is actually B inverse n into I comma q into x q, right. So, x q is a scalar, okay. So, I will rather write it like this, that would be better. It is B inverse n 1 comma q. So, B inverse n is a matrix 2 comma q dot B inverse n m comma q, okay. So, you would have got more differences like this if you had the other x's also to be non-zero, but since only x q is non-zero, right. So, you will have minus x q into this matrix, okay. So, I have done nothing, I have expanded x b equal to B inverse B minus B inverse n into x n, where x n is consisting of all 0 vectors except x q could possibly be non-zero, okay. In that case, x 1 to x m should be written of this form, okay. Note that if you increase x q, okay, so that is something that we are going to do, right. So, because it is if x q is actually going to become a basic variable, okay, then I am possibly going to increase it from 0, right. So, that is why I am actually have made it a basic variable, right. So, if I increase that, I should take care that none of the erstwhile basic variables becomes negative, right, because we have the constraint x non-negative, right. So, I should take care that x1, x2 dot 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 xm is actually greater than or equal to 0, right. So, in other words, I want B inverse n of I minus x q into B inverse B of I minus x q into B inverse n of I comma q must be greater than or equal to 0, right. Okay. So, I will write it as this way, yeah, B in x q is a scalar, please recall, B inverse B is a vector, B inverse n is actually a matrix, but since I have just taken the qth column, it is a vector, okay. So, I comma q is a scalar, okay. So, this must be greater than or equal to 0 for all I in 1 to m, okay. So, B inverse B of the ith component of B inverse B minus x q into the I comma qth component of B inverse n should be greater than or equal to 0, okay. So, this is something that we require, okay. Now, let us try to find a constraint on x q based on this, okay. So, if B inverse n of I comma q is greater than 0, then yeah, so when you rearrange this, you have B inverse B of I greater than or equal to x q B inverse n I comma q, and this implies that x q is less than or equal to B inverse B of I by B inverse n of I comma q, okay. So, yeah, I can do the division because B inverse n of I comma q is actually positive, okay. So, I cannot do that if it is negative, because yeah, the sign will flip, right, okay. So, fine, yeah, if B inverse n of I comma q is positive, then we have this expression that x q must actually be less than or equal to B inverse B of I by B inverse n of I comma q, okay. So, but what happens if B inverse n of I comma q is less than 0, okay. So, yeah, so suppose your B inverse n of I comma q is less than 0, okay, then the particular value of x is only going to increase, right. So, suppose B inverse n of 1 comma q were negative, okay. So, I do not need to bother about x1 being 0, because x1 was positive initially. Now, that I am going to increase x q and B inverse n of 1 comma q is negative, x1 is certainly going to increase. So, I do not need to care about those i's for which B inverse n of I comma q is negative, right. So, what I am going to do is I am going to only consider those i's, okay. So, I define the index set I, which is I such that B inverse n of I comma q is greater than 0, okay. So, for all those I, okay, I want, so we want x q less than or equal to B inverse B of I by B inverse n of I comma q for all I in capital I. For the others I do not care, okay. Now, if one of the i's has to become 0, So, only if it becomes 0 it becomes a non basic variable, right. If everything is positive, then it is not a vertex, right. So, you want one of them to become non basic, and which will actually become non basic? It is that I for which this quantity is the minimum. Okay. So, yeah, you can say that. So, the variable that would become 0, variable I would write, variable I that would become 0 is argmin over I in I of B inverse B of I by B inverse n of I comma q. Okay. So, this is the variable that, so suppose this is j, let us say variable j that would become 0 is this. Okay. So, x j would become non basic in the next iteration. Okay. Now, we have the full algorithm ready. Okay. So, note that it has taken like about 3.5 lectures just to arrive at what the algorithm that needs to be there. Okay. So, to put it in a nutshell, when we are given a linear program of a particular form, we convert it into the standard form. Okay. And then first choose a vertex. How do we choose a vertex? We pick m linearly independent vectors from the standard form matrix A, okay, and fix the solution as B inverse B comma 0. Okay. Then we check whether that vertex is indeed the minimizer or not. So, that is a method. If it is the minimizer, we stop. If it is not the minimizer, then we exchange a variable between the set of basic variables and the set of non basic variables. Okay. So, now we have got another set of basic variables and another set of non basic variables, right. So, that is another vertex to be precise. Okay. We again check whether it is the minimizer or not. If it is not, then we again perform the exchange. We check if it is a minimizer. If it is not, we continue. Okay. So, we stop when we actually get to the vertex which is indeed the minimizer. Okay. So, I will write down the algorithm now. Okay. The simplex algorithm by Danzig, if you remember the name still. Okay. So, the first step is to convert the given LP into the standard form min C transpose x subject to A x equal to B, x greater than or equal to 0, where A is a matrix of full row rank. Okay. So, this is actually a step that you have to do by hand. Okay. So, I mean you have after doing the conversion, you actually feed the values to the computer, right. So, keep that in mind. Okay. The first step is actually, I mean, though I write it as an algorithm, this is something that you have to do by hand. Okay. All right. Now, the second step is to choose m independent columns of A, the variables corresponding to independent columns, x b are basic variables, others are non basic, others x n are non basic. So, the solution x b star x n star, which is b inverse b comma 0 with b inverse b greater than or equal to 0 is a basic feasible solution, okay, BFS. So, this is a term that you would find repeatedly in literature relating to simplex algorithm. Okay. So, it is good to note that down. Okay. So, basically a basic feasible solution is a vertex. Okay. All right. So, yeah, the after this, yeah, I will go to the next page. So, you have a loop now, while C n transpose minus C b transpose B inverse n is yeah. So, if this is not completely greater than or equal to 0. Okay. So, yeah, let me write it this way: I less than 0 for some I. Okay. So, that is there exists an I for which C n transpose minus C b transpose B inverse of n, B inverse n of I is actually less than 0. Okay. When that happens, yeah, you are still in the loop. Okay. Otherwise, yeah, you move out of the loop basically. Okay. So, when this happens, you need to perform the exchange. Okay. So, how do you perform the exchange? You do the following. So, you make so let q equal to argmin I of C n transpose minus C b transpose B inverse n of I. Okay. So, whichever the minimum element of this vector, that is what you call as q. Okay. And let I be the set of all indices for which B inverse n of I comma q is greater than 0. Okay. Now, J is argmin over I in I B inverse B of I by B inverse n of I comma q. Okay. So, now that you have got q and j, so it becomes make x q basic and x j non basic. Okay. So, x q was a non basic variable, it has now been made a basic variable. X j was a basic variable, it has now been made a non basic variable. Okay. So, okay. So, yeah, and you can again continue this. So, because now the set of basic variables and the non basic variables have changed, your C n, C b, B and n everything also changes, right. So, yeah, so the loop continues. Okay. So, after you come out of the loop, okay, yeah, you have a certain value of basic variables and certain of non basic variables, right. So, the solution is yeah, x b star x n star is b inverse b comma 0. So, yeah, that is basically the simplex algorithm. Okay. So, there is one case that I have not discussed in the lead up to the algorithm that we have had, right. So, that is, what if the set capital I, what I have written here, right, that is empty. Okay. So, that is possible as well, right. So, what happens if okay, so that is another question. What happens if, yeah, the set of i's for which B inverse n I q greater than 0 is actually empty, that is, yeah, is empty. In other words, every element of this column B inverse of n, the qth column of B inverse of n, right. So, every element in the qth column of B inverse of n is actually non positive, it is less than or equal to 0. Okay. So, in that case, yeah, I mean you cannot find j, right, because I itself is empty. So, what does arg min B inverse B of I, B inverse of I q mean, right. So, actually I claim that in that case the problem is unbounded. Okay. So, why is that the case? Because please note that, so what we are saying is that every element here, every element in this vector what you have, right, this vector, the last vector B inverse n 1 comma q, B inverse n 2 comma q dot dot B inverse n n comma m comma q, everything is less than or equal to 0, right. So, what happens if you increase x q from 0? You can see that all of this becomes positive or actually non negative, right. That means as you increase x q, the values of x1 dot 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 xm keeps on increasing, right. So, if it keeps on increasing, there is certainly no bound for the values of x1 to xm, and because of which the objective function becomes unbounded, right. So, I mean you cannot make any of the variables x1 to xm as 0, right. So, it keeps on increasing and everything is feasible, right. So, if you keep increasing, and I mean the polytope is in such a way that it is actually feasible, right. So, the problem actually becomes unbounded. So, that is also something that needs to be added in the algorithm, right. So, we have to say that if I is empty, okay. So, yeah, so in this step, if I is an empty set, then yeah, so we have to print unbounded and exit, okay. So, this is possibly one step we have to write in between, okay. So, I will give examples of all such cases, okay. I mean if you consider a particular linear programming problem, there are possibilities that it can actually be unbounded, right. So, I mean constructing an example is not very hard. If you want an immediate example, okay. So, I can consider this particular example. Let us say you want to let us say we will maximize x1 plus x2 such that x1 plus x2 greater than or equal to 1, x1 x2 greater than or equal to 0. Okay. Just by looking at the problem you can say that, yeah, so the value of x1 plus x2 is infinity, right, because I am saying x1 plus x2 greater than or equal to 1. So, yeah, any number, any x1 and x2 for which yeah, it is greater than or equal to 1, say 100 comma 100, 1000 comma 1000, 1 billion comma 1 billion, 10 power 100 comma 10 power 100, everything belongs to the feasible set, right. So, you can keep on increasing the value of x1 x2 until it reaches infinity, right. So, there is no bound for the maximum value of x1 plus x2, right. So, yeah, this is a clear example of a linear programming problem which is giving us an unbounded answer. Okay. So, we might be given a problem of this sort and simplex algorithm is expected to handle that too, right. So, if you apply all the steps of simplex algorithm, you will see that yeah, the problem will be unbounded. Okay. So, yeah, this is the exact form of the simplex algorithm. We will learn how to code this particular algorithm in the next lecture. Thank you.